Hi everyone, it's Mr. Bowman, and in this video we're going to do some free response problems that focus on position, velocity, and acceleration. We are also going to take a look at some applications of the intermediate value theorem and the fundamental theorem of calculus. So our first problem is a no calculator problem, and it tells us that two particles move along the x-axis for the closed interval from 0 to 8, meaning that that includes those endpoints. The position of particle P at time t is given by xp of t, while the velocity for particle Q at time t is given by vq of t. It also tells us that particle Q is at position 5 at time t equals 0. So part A asks, for time from 0 to 8 inclusive, when is particle P moving left? A reminder that particles are moving in the negative direction, which is left or down, when the velocity is negative, and moving in the positive direction, which is up or right, when the velocity is positive. So in letter A, we do not have a velocity function for p, so we're going to find that vp of t by taking the derivative of xp of t, x prime of p of t, and that would be 1 over what we are taking the natural log of, t squared minus 2t plus 10, times the derivative of the inside, which is 2t minus 2, which we would write, or could write, as 2t minus 2 over t squared minus 2t plus 10. To figure out where vp of t is positive or negative, we would probably make a sign chart, and that would require us to figure out where the denominator is positive or negative and the numerator. So the first thing I would do is try and factor the denominator. Turns out that it is not factorable, and it is a quadratic that opens up. So if we were to think about b squared minus 4ac, we would see that that's negative, and that tells us that that quadratic never touches the x-axis. So it lies entirely above the x-axis. Therefore, it is always positive, which actually simplifies our sign chart. So our sign chart has to include the endpoints of 0 and 8, but we're only going to have a sign change where the numerator changes sign, and the numerator, 2t minus 2, is 0 at t equal 1. So I'm going to label this as vp of t, and that's the sign chart. Now we just have to fill it in. Pick a value between 0 and 1, like 1/2, put it in the numerator, and you get a negative result. A negative divided by a positive is a negative. Pick a number between 1 and 8, like 4, put it in the numerator, divide it by a positive denominator, and you have a positive result. So to answer A, P is moving left on the interval from 0 to 1 because vp of t is less than 0. You will notice that I included 0 in my interval, and the reason I did that is because if you plug 0 in to the numerator, you get a negative number divided by a positive number, so the velocity of particle P is also negative at 0. I did not include 1 because the velocity is 0 at 1. In terms of the scoring, we get 1 point for finding the derivative and 1 point for the interval. Part B of this question asks, over the same interval from 0 to 8 inclusive, find all times during which the two particles are traveling in the same direction. They're traveling in the same direction when their velocities have the same sign, so we're going to have to make a sign chart for vq of t, and vq of t We're going to make this sign chart right below that, just so we can line them up. VQ of t is given by t squared minus 8t plus 15, t squared minus 8t plus 15, and it turns out that that is factorable. It factors into t minus 5 times t minus 3, so this velocity function has zeros at 3 and at 5, and we're going to fill out this sign chart. So pick a number less than 3, like 2. Both factors would be negative. Negative times a negative is a positive. Pick a number between 3 and 5, like 4. Plug it into both factors. One factor is negative, one is positive, so the result is negative. And then pick a number between 5 and 8, like 7, and both factors are positive, so the product is positive. So where do the two velocities have the same sign? This is why I like lining them up, because I can draw these vertical lines and look at the various time intervals and see where they are equal. So the first thing we're going to do is figure out where they're equal. Positive, negative, and positive, positive. So the particles are traveling in the same direction anywhere their velocities have the same sign. I have a mistake here for VQ of t. That should be positive right there. So they are traveling in the same direction over the intervals from 1 to 3 or from 5 to 8, because VP and VQ are the same sign. So let's take a look at the scoring for that. The scoring for that, basically giving the intervals and analysis using both of the velocities. And they are from 1 to 3 and 5 to 8. You will notice I made a mistake here. I did not include 8, but I should have, because at t equal 8, both the velocities are going to be positive, so I'm going to go back and fix that. And that's a good reminder that when you have closed intervals, when you include the endpoints of the intervals, you need to think about checking the endpoints of the intervals when you're writing solutions to your problems. Part C of this question says, find the acceleration of particle q at time 2. Is the speed of particle q increasing, decreasing, or neither at time t equal 2? Explain your reasoning. So the speed of a particle is increasing if the velocity and the acceleration have the same sign, and decreasing if they do not have the same sign, if they have opposite signs. So we're going to find the acceleration of particle q at time 2. In part C, AQ of t is equal to V prime of q. So that is going to be the derivative 2t minus 8, the derivative of VQ of t, and AQ of 2 turns out to be 4 minus 8, or negative 4. VQ of 2 turns out to be, we're getting that from right up here, VQ of 2 turns out to be 4 minus 16 plus 15, which is positive 3. So particle Q is slowing down. Let me rephrase that. The speed of particle Q is decreasing at t equal 2 because AQ of 2 and VQ of 2 have opposite signs. So let's take a look at the scoring rubric for that. Find AQ of 2. We get a point for that and a reason for the speed decreasing. And the last part of this problem, find the position of particle Q the first time it changes directions. Well, when does particle Q change directions the first time? By looking at our sign chart for VQ of t from part A, we can see that particle Q changes directions for the first time at t equal 3. So this is going to be our application of the fundamental theorem of calculus, and basically it goes like this. If we integrate from 0 to t VQ of, we're going to use the dummy variable x, we get the antiderivative of the velocity, which is the position, xq of t minus xq of 0. And the reason I picked 0 to t is because at t equals 0, we know the initial position is 5. That was actually given to us. So we can solve this equation for xq of t and get the integral from 0 to t of vq of x dx plus 5 is what we're looking for. We want to find the position at time 3. So xq of 3 is equal to the integral from 0 to 3, and the velocity function is x squared minus 8x plus 15 dx, and then we're going to add 5 to that. So if we anti-differentiate that, we have 1/3 x cubed minus 4x squared plus 15x from 0 to 3, and we're going to add 5 to that, and if you evaluate this, you will see that you get 23. So let's take a look at the scoring. 1 point for the antiderivative, 1 point for using the initial condition, and 1 point for the final answer.